Okay, welcome to part 3 of the Functions as Series video series. Let's go ahead and dive in. So we've been looking at the geometric series, and we saw that as we get infinitely many terms, we converge to this formula here, this a1 over 1 minus r, on the condition that the r is less than 1. And we're going to use that to create a new set of series here. And recall that we substituted in x as if it was an r. So we have this common ratio here of negative x, meaning it is indeed geometric. And as we take infinitely many terms, we get the sum of a1 over 1 minus r. Now, what's nice about that is we've converted a power series into a function. And that function is 1 over 1 plus x. And I'm going to use that 1 over 1 plus x to take the antiderivative of it, because I know the antiderivative of 1 over 1 plus x is natural log 1 plus x. And knowing that these two things show equality, the power series and the function, I'm also going to take the antiderivative of the power series. And when we do that, we're going to end up getting, a series of power rule antidifferentiations, because this is just a polynomial. And we've now leveraged the power of a geometric series to find a power series for the natural log. It's a really powerful technique. Now, the thing that we have to keep in mind here is there's a c, as with any antidifferentiation, and we're going to plug in 0, because 0 is the easiest value to compute, and we get that 0 plus c is 0. The natural log of 1 is 0. So therefore the c is 0, and you'll notice that c is going to disappear in my final line here. And this is a power series that you need to memorize. It's one of the many formulas that's worth knowing for power series and functions. Natural log is one, but we'll be looking at several throughout this video series. Now, we do have this condition, of course, that the r, absolute value of r, is less than 1. And that condition is going to stick all the way through. So our last line here says the natural log of 1 plus x is equal to this power series. That is only true from negative 1 to 1, stemming from our geometric series limitation. So let's observe that in action in our Desmos file. So here we have a Desmos file going where I have my natural log of 1 plus x. I have the asymptote at x equals negative 1. And you'll see here that my partial series, as I keep adding more and more terms, becomes more closely matching my functional, the curve. So this is only at 4 terms. Of course, 4 is not very many. And I don't want to type out 30 or 40 terms. It becomes monotonous. So I use my summation notation and a slider, and we can very quickly add as many partial sums as we want. So if we keep sliding out, at the 10th partial sum, 12th, 15th, these all start to look pretty good. And I go all the way out to 50, and we're starting to see in between negative 1 and 1, it's almost an identical match. Now, why stop at 50? We want infinite, but we do have the limitation of processing power. So you'll notice here that as I increase to 100, my computer's struggling to keep up with my slider. So there's a processing power delay here. And even at 100, it's starting to get close to this 1 and this negative 1. We do always need to take a look very carefully at the endpoint. So the question is, of course, do we include the actual endpoint of 1 and negative 1, or is it a non-inclusive interval? And if we look at negative 1 exclusively, we know that negative 1 has an asymptote for my function, while this is a polynomial and it cannot have an asymptote at negative 1. Polynomials don't have asymptotic behavior. So if negative 1 is leading to a vertical asymptote on the function, it cannot converge to a polynomial. So -1 will not be included in our interval. That's, of course, not the test we're going to use. We're going to use a much different test moving forward. The case of =1 is a little different because, it's hard to tell if it's going to explode at 1 and diverge or include at 1. So let's dive into our next frame here. So what do we do about boundaries? You're always going to want to test boundaries separately. So here you'll see I'm actually testing -1. I'm plugging that into every value of x. And when you do that, you'll end up getting just this negative, 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 negative as you match up the powers of -1 here. Now, this is the harmonic series. And from previous videos and studies, you've seen that the harmonic series diverges. If you need a review of why that is true, you can always look up the p-series test, the integral test, or the comparison test. And I may link videos to proving these in a later video. So because when we plug in -1, we get a divergent series, we are not going to include -1 in the interval of convergence. Now testing x = 1. If we plug 1 into every value of x, we get this alternating harmonic series. And we know that any alternating series in which the individual terms approach 0 should converge. So because when we plug in 1, we get the alternating harmonic series, which converges, we are going to include 1 in our interval of convergence. Therefore, putting it all together, we have a function, natural log of 1 plus x, that is represented as a power series that has all of the powers divided by the powers in the denominator. And we are not going to include -1, but we are going to include 1 on our boundary, our interval. So moving forward, I have a practice set for you. You are going to try to create a power series for the arctangent function, writing out the first 4 terms, the general term, and the summation notation form. Determine the interval of convergence. Test the endpoints. Do you need to include the endpoints or not? And you're going to build a Desmos animation that shows your partial series converging to your arctangent function. And that's more for you to test your answer. If you see that your Desmos file tends to justify your solution is correct, well, you're probably doing it well. For hints, if you don't want the hint, close your eyes, shut your ears. For hint 1, think of a geometric series that represents a function related to arctangent. So use your knowledge of calculus. How does arctangent possibly get you a geometric series function connection? And if you need another hint, you can always look to the previous video where the series is actually inside of part 2 of the video. So that's a pretty eye-opening hint there. Okay. Solutions. If you haven't already tried this yourself, make sure you pause the video, go back, try it on your own before you look here. So recall that the antiderivative of 1 over 1 plus x squared is the arctangent of x plus c. Knowing that, well, 1 over 1 plus x squared, I can rewrite plus as a minus a negative, and now I have that a1 over 1 minus r form. That gives me the geometric series of starting at 1 with a negative x squared as r, and the limitation, of course, that r absolute value is less than 1. So now take this antiderivative from the left side of the equality, take the antiderivative of the right side of the equality, and you end up that the antiderivative of 1 over 1 plus x squared is arctangent x plus c. The antiderivative of this series is sitting here, and we do need to find out c, so we plug in 0 across the board, and we end up getting that c is 0. Recall the arctangent of 0 is 0. So now we have a series for arctangent that is alternating signs, every odd power divided by that power. And this has the limitation, of course, that x is between -1 and 1. So we have a Desmos animation file to show that that is true. So here's my arctangent function. Notice I've arranged them in folders for organization. If we look here at our partial sums seem to be getting to be closer and closer approximations. I turn on my summation notation for optimization. So now we can see as 30 partial sums. Well, that seems pretty good match in between the interval here. Now, of course, the question becomes down to, do I include that boundary and that boundary in my function? So can I include the value of x equals 1? And this is going to lead us to a nice, interesting exploration in the next video. Because we know the output of 1 is pi over 4, that's going to lead me to some sort of series for pi, hopefully. And we'll look at that in the next video. So how do we know if we include 1 or do not include 1? We go back to our testing of each case. So do I include -1 in the boundary? So -1, plug into each x. Notice that -1 cubed is negative, negative times negative is positive, -1 to the 5th is negative, negative times positive is negative. So in doing that, we plug in -1 and we get an alternating series. Alternating series with terms approaching 0 converge. That's the alternating series test. So because we plug in -1, it converges. Then we include it in the interval of convergence. Again, we test the x equals 1 boundary, plug in 1, we get another alternating series. So because x equals 1 causes a convergent series, we include it in the interval of convergence. So now we have that the arctangent of x can be represented by a power series that is alternating and has all the odd powers divided by that power. And there's a -1 to the k minus 1 missing here. So include that in your notes. All right, thank you. And in the next video, we'll be looking at a exploration of the natural log of 2 and of pi. So it should be a very exciting video. Okay, see you there.